All right, let's dive in. Today, we're going to crack open that AI black box and look at a pretty simple idea that honestly changed everything. It's called the multilayer perceptron. This is the reason AI can do more than just draw straight lines, and if you want to understand how deep learning really works, this is where it all starts.
So let's just kick things off with this question, because for a really long time, this was a massive roadblock for AI. I mean, how do you teach a machine to solve a problem that's messy, that's complex, and that you can't just neatly divide with one simple line?
To really get why this was such a breakthrough, we first have to understand the brick wall that early AI ran right into. We're going to look at a problem that just completely stumps a basic model, and that's going to set the stage for why we needed a whole new way of thinking. Something that could actually handle the messy, nonlinear world we live in.
Okay, so on the one hand, you've got a simple problem. Think about separating red dots from blue dots when they're all on opposite sides of a map. Easy, right? You just draw one straight line down the middle. A basic AI, a single-layer perceptron, can do that all day long. But then, you get the problem on the right. This is the classic XOR problem. It's like a checkerboard. Now you try it. No matter where you draw a single straight line, you are never ever going to be able to separate the red squares from the black ones. For a simple AI, this isn't just hard, it's literally impossible.
And that, right there, is the whole issue. This one limitation, the fact that it could only think in a single, rigid, straight line, was a huge hurdle for AI research. It was a dead end. To move forward, we needed something totally new.
And this is where things get really interesting, because the solution, it turns out, was a pretty small change to the model's design, just adding something new in the middle, and suddenly, boom, a massive breakthrough in what AI could do.
So let me introduce you to the hero of our story, the Multilayer Perceptron, or MLP. Now you can think of it like a company. That old simple model, that was like a single boss trying to do everything on their own. The MLP, though, it adds hidden layers. This is like giving the company a whole team of middle managers. They can analyze complex parts of a problem and then pass their findings up the chain.
Okay, let's build one of these things piece by piece. First up, you've got the input layer. Think of this as the front door. It's where all the raw data comes in. It doesn't do any thinking, it just receives the initial info, like the coordinates of the dots on our checkerboard.
Next up is the magic ingredient, one or more hidden layers. Now, these are the middle managers I was talking about. They aren't just passing info along, they are actively transforming it. Each little part of this layer, each neuron, is like a specialist looking at the data from a different angle, hunting for more complex patterns. This is where the real deep thinking happens.
And finally, at the very end, we've got the output layer. This is the CEO's office. After all the hard work and analysis from those hidden layers, this layer takes everything they found, puts it all together, and makes the final call. It gives us the answer.
So really, the crucial point here, the thing that gives the MLP its power, is these hidden layers. Each neuron in there performs what's called a nonlinear transformation. Now, I know that sounds super technical, but here's a simple way to think about it. It's like giving the network a flexible, bendy ruler instead of a rigid, straight one. It can now bend and curve its understanding to create complex shapes that actually fit the data instead of being stuck with that one useless straight line.
Okay, so we've got the structure down, but how does one of these things actually, think? It all starts with a process called the forward pass.
The forward pass is basically the network's first thought. Information flows in just one direction, from the input, through those hidden layers, and all the way to the output. It takes in the data, it crunches the numbers, and it makes an educated guess. You can think of it like the network's first draft of an essay. It's probably not perfect, but it's a start. And let's be real, a brand new, untrained network, it's going to be wrong. A lot. So what happens then? Well, this is where the real magic happens. This is where the learning actually kicks in. The network literally uses its own mistakes to get smarter. So, this network has this incredible process for learning from its own errors. It's an algorithm that is, and I'm not exaggerating, the absolute bedrock of all modern deep learning. It's called backpropagation. Okay, I know, that's a bit of a dense quote. So what does it actually mean in plain English? At its core, backpropagation is just a feedback loop. The network looks at how wrong its guess was, and then it uses that exact information to go back and tweak its internal wiring so it does a little bit better the next time.
The best way to think about it is like a performance review for those middle manager neurons. First, it measures the error. How far off was the final decision? Then, it sends that feedback backward through the company.
telling each middle manager neuron how much it contributed to the mistake. And finally, it adjusts the connections, the weights, of each neuron. It's basically telling them, hey, your strategy was a little off. Tweak it just a tiny bit so we're closer to the right answer next time.
So the network just keeps repeating this cycle. Forward pass, check the error, send feedback backward. Over and over. Thousands, sometimes millions of times. It's just this relentless process of trial, error, and tiny adjustments. So after all of that training, what happens to our impossible checkerboard problem?
Well, it becomes solvable. The problem that was once totally impossible is now, honestly, a piece of cake for our trained MLP. It can classify all those checkerboard points perfectly, something its simpler ancestor could never, ever do.
And this, right here, is the MLP's superpower. It's not stuck with that one straight line anymore. By combining all those tiny calculations from its hidden layers, it creates what's called a nonlinear decision boundary. It essentially learns how to draw a complex, squiggly shape that can perfectly snake its way around the different groups of data, separating them cleanly. It finally solves the puzzle.
And that, right there, is the big takeaway. If you remember just one thing, it's this. That single change, adding hidden layers, is what gives neural networks their incredible power. It's the difference between being able to solve only the simplest puzzles and being able to learn the complex, messy, nonlinear patterns of the real world. This is the foundation of all modern AI.
And that really makes you wonder, doesn't it? The MLP is one of the most basic building blocks in deep learning. So if this relatively simple idea of just adding more layers can unlock so much power, just imagine what else we can build on top of it. What other impossible problems are now suddenly within reach? The possibilities are pretty staggering.